You've seen it at freight depots, heard it from your car window near the tracks. Locomotives parked in long rows, every single one of them running, diesel exhaust drifting up into the night sky. They're not moving. They're not pulling trains. They're just sitting there, burning fuel. Why would a railroad company, obsessed with operating costs down to the penny, leave engines running all night? What breaks if they shut down? Is someone even inside? The answer isn't laziness or oversight. It's physics, economics, and a 70-year-old engineering compromise. But the real reason goes a lot deeper than fuel economy. Here's the thing most people miss. A diesel locomotive isn't just a big engine on rails. It's a mobile power plant, a compressed air factory, and a machine built around a 16-cylinder diesel engine that has very specific feelings about being shut off in the cold. First, the locomotive serves as the electrical heart of the entire train. It powers the control systems, the communication equipment, the diagnostic computers. But more importantly, it's generating and maintaining compressed air for the entire train's braking system. That's not optional equipment, that's federal safety regulation. When a locomotive shuts down, the air pressure in the brake lines starts dropping. A fully loaded freight train can stretch over a mile long with 100 or more cars. Rebuilding air pressure through that entire length takes hours. If a crew needs to move that train and the air system is depleted, they're looking at a 3 to 4 hour delay just to get brake pressure back to operational levels. And here's where people get it wrong. The common reaction is just restart it in the morning like a car. That's what works for everything else. But a diesel locomotive isn't a Honda Civic, not even close. Diesel locomotives use compression ignition. No spark plugs. They compress air so hard it heats up enough to ignite fuel on contact. That process depends heavily on the engine already being warm. A cold start in freezing temperatures means incomplete combustion, excessive smoke, extreme wear on cylinder walls, and strain on components before the oil has even circulated properly. A practice widely understood among railroad maintenance crews, though the exact figures are debated, is that a cold start below freezing puts wear on a locomotive engine equivalent to several hundred miles of normal operation. That's like adding an entire day's worth of revenue service before the locomotive even leaves the yard. Every cold start in winter is a small mechanical trauma, but engine wear is actually the secondary concern. Here's the first. Locomotives carry between 200 and 400 gallons of coolant. Not the 1 or 2 gallons in your car. Even with antifreeze mixed in, extreme cold can cause coolant to gel, or, in the worst case, freeze solid in the engine block. A cracked engine block on a locomotive is a $50,000 to $200,000 repair. The locomotive is out of service for weeks. The idle keeps the coolant circulating and warm. It keeps the engine above freezing. It keeps the machine alive in a very literal sense. But there's another layer most people never consider. Locomotives use massive battery banks to start the engine and power systems when the engine isn't running. These aren't car batteries. They're industrial battery arrays weighing hundreds of pounds. In cold weather, battery capacity drops dramatically. A locomotive that sits overnight in sub-zero temperatures without the engine running to recharge the batteries may not have enough power to restart in the morning. So the idle is partly a battery management necessity. Then there's the regulatory framework. Canada's locomotive idling regulations explicitly allow idling beyond the standard 30-minute limit when necessary to prevent engine damage from freezing temperatures, maintain brake system air pressure, or keep batteries charged for reliable restart. So the locomotive idling overnight isn't an oversight. It's following federal safety rules while legally navigating operational exceptions written specifically for these engineering constraints. One parked locomotive, 2 sets of rules, both applying at the same time. Now here's the part that sharpens the picture. Not all locomotives face this problem equally. Switcher locomotives working in mild climates, the ones doing yard work and going back to heated maintenance facilities every night, can shut down safely. Park, lock, walk away. But long-haul road locomotives operating through Montana in January or Northern Ontario in February live a completely different reality. That engine running overnight is the difference between a train that moves in the morning and a train that sits dead on the tracks for half a day. The solution the rail industry developed is called an auxiliary power unit, an APU. Think of it as a small diesel generator, roughly the size of an industrial air conditioner, mounted on the locomotive. It runs the electrical systems, maintains battery charge, and keeps critical components warm without firing up the main engine. Cleaner, more efficient, smart engineering. But here's the catch. An APU installation costs between $150,000 and $300,000 per locomotive. That's a generator system that costs as much as a house. Not every railroad, especially smaller regional carriers operating on thin margins, can absorb that capital expense across an entire fleet. So the main engine keeps running. The math is brutal. Idling burns roughly 1 to 2 gallons of diesel per hour, depending on the locomotive model. At current prices, that's $4 to $8 per night. Across a fleet of 500 locomotives in winter operations, that adds up to millions of dollars per year in fuel just for staying ready. The APU exists entirely because of that math, but not everyone can afford the solution yet. There's also shore power infrastructure, basically industrial electrical outlets at rail yards that let locomotives plug in like a phone charger. The engine shuts down. The locomotive draws power from the grid to run systems and maintain heat. But here's the problem. Shore power requires infrastructure investment at every yard, every siding, every maintenance facility along thousands of miles of rail network. The build-out is happening, but it's slow. A locomotive on a long-haul route through rural Wyoming isn't parking at a facility with shore power. It's parking wherever the crew's hours run out. This is the part everyone misses. Locomotive idling hasn't always looked like this. Go back to the steam era. Steam locomotives never had this problem. The firebox stayed warm as long as there was coal and water. Crews would bank the fire overnight, keep a low burn going, and the locomotive was ready to move in the morning. Simple, reliable, no battery concerns. But then, dieselization swept through North American railroads in the 1950s and 1960s. Diesel locomotives were more efficient, required less maintenance, needed smaller crews, but they introduced a new problem: cold starts. Early diesel engines were even more brutal about cold starting than modern designs. Engines would fail to turn over. Coolant would freeze. Batteries would die. So the practice developed. Leave them running. It became standard operating procedure, taught to every new maintenance crew, baked into railroad culture. And here's the problem with deeply baked habits. They outlast the original severity. Modern locomotives have better cold start systems, synthetic oils, improved battery technology. But the behavior stayed. Some of it is still necessary. Some of it is institutional inertia. The line between the two isn't always clear. Here's the surprise. You've been touching this system your whole life without knowing it. That bag of rice in your pantry. It rode in a hopper car behind a locomotive that idled overnight at a grain terminal in Kansas. That coal-fired power plant keeping your lights on. The coal arrived on a unit train, whose locomotives ran all night at the loading facility. The steel in your car, the lumber in your house, the chemicals in your cleaning products. All of it moved by rail, and all of it depended on locomotives that stayed running when they weren't moving. The fertilizer that grew your food traveled through the winter behind idling locomotives. the propane tank at your cabin, rail delivery, idle-dependent logistics, that distant train horn you hear at night from your bedroom. That's a locomotive that will idle for 10 hours at the next crew change point, keeping systems alive, waiting for the next shift. Now for the real trade-off. Diesel exhaust from idling locomotives isn't nothing. It puts particulate matter and nitrogen oxides into the air near rail yards and communities close to freight corridors. That's a legitimate environmental concern, and residents near those facilities have every right to push for solutions. A fleet of 500 locomotives idling 8 hours a night burns roughly 4,000 to 8,000 gallons of diesel while going absolutely nowhere. But here's the context. Rail freight is 3 to 4 times more fuel efficient per ton mile than trucking. Moving that same freight by truck would burn far more fuel and produce far more emissions overall. The good news is the industry is actively evolving. Tier 4 emission standards from the EPA pushed locomotive manufacturers to develop cleaner engines with better fuel efficiency. Automatic engine shutdown systems now exist that monitor temperature, battery charge, and brake pressure, shutting down the engine when conditions safely allow and restarting automatically when needed. Hybrid locomotives are entering service with large battery packs that assist the diesel engine and can power hotel loads, the railroad term for electrical systems, during idle periods. Shore power networks are expanding along major corridors. The idling habit is genuinely shrinking, but it's shrinking slowly because the gap between we have better technology and every railroad can deploy it across 25,000 locomotives is still wide. So here's where you land. You drove past that rail yard thinking you were looking at waste, negligence, a bad habit that nobody bothered to fix. But what you were actually looking at was a brake system air pressure requirement, diesel engine physics, a battery bank that needs constant charging, coolant that can freeze and destroy a $200,000 engine, a regulatory framework with explicit operational exceptions, and a 70-year-old engineering compromise with very logical roots. That sound you used to find annoying, that low rumble echoing across the yard at 2 a.m., that's the hum of the system that moved the grain in your cereal this morning. And if you think locomotives are complicated, wait until we talk about why railroads still use air brakes, a technology invented in 1872, instead of something modern.